Yeah, let's get started. My name is Srinivas Palthepu. I work for Capital One. I work in big data engineering teams. And today I'm going to talk about one of the projects we have been doing. It's called real-time analytics on customer activity data using something called Apache Flink as a core component, but we use a bunch of different open source tools. Uplink is just one of them. So, but it's new and something unique. So I just put it on the title. That doesn't mean that that's the only tool. So there are lots of different tools need to work together. So here is the agenda. We'll just spend a little bit time about Capital One. As pretty much everybody knows about as a bank, but there is a little bit more to it than just a bank. And I will go over how the analytics has done for last few years, like a few decades probably, and how that is changing, and how the paradigm shift is happening with the new technologies, and what are the different drivers which are pushing this new paradigm shift. And then I will introduce the Flink very briefly. I don't want to spend too much time in describing the tool because that's not the goal of the talk. Here I want to describe the business use case. If you are interested in learning more about the Flink, I will provide some references and also you can reach out to me later. But I just have like 1 or 2 slides, give you a brief overview of that. And then I will describe our use case, how we use the Flink as a tool to achieve what we wanted. And then we have some concluding remarks. So briefly about Capital One, it's a bank, so that's nothing new in that. But it's a bank like no other bank. In a sense, it's very heavily technology driven. Technology is central to the banking, not as a periphery like traditional banks consider that as an enabler, but we build business processes around the technology. So it's not like a bank lot of history. It is very recent compared to like hundreds of years of the banking history you have seen other banks, but it's pretty fast growing. The main point to realize here is that we have lots of customers and we have lots of data. So that's what I'm trying to get at the end. So we have 65 million customer accounts and we collect a lot of data. So bank, essentially what is a bank? Bank is essentially a big machinery that handles and processes and moves money. Right? And money is digitized. Now money is nothing more than data. And so when money becomes data, bank becomes a data processing engine. So that is the bottom line. So at the core of our banking industry, we have a complex system of data processing, data moving elements that kind of make the whole banking work in this modern world. So Capital One sees itself as a software engineering company. It happened to provide financial products as a business, similar to the Amazon treats is a technology company, but its products is a retail. So a few of the things which differentiates our bank is it's the first bank to go to cloud. I don't think any other bank put their applications in the cloud. So we committed to completely migrate to cloud by 2020. So we already started in a big way. And first bank to contribute the code to open source. A lot of banks use open source based products, but I've not known, at least as far as I know, there is no other bank employees contribute code to open source, whereas Capital One employees contribute back to open source. And we also support a lot of technology engagement. Local communities, we hold meetups, we hold hackathons, and we engage with the local community heavily in various centers. And we want to also drive the technology and innovation as well, not just a consumer of it. So that's the reason strategically we adopt the open source model, because it's not just a cost or a price. That's probably one of the elements, but that's not the main point. So main selling point of the open source is that it opens our engineers to innovate on top of it, whereas if it is a commercial product, we are at the mercy of the vendor all the time. So that's just a little bit about the Capital One. Let's get out of the way. So let's look into the main topic here. So let's look at what's the traditional batch analytics, how we have been doing last 30-40 years. And then see how that looks like and what is that called CSAD cycle. I'll describe what that is, and then see what are the limitations, how those traditional approaches are not helping in new world. So this is a kind of a high level view of how we have been doing analytics. We have applications on the left side that generates data as a part of their business transactions. and whatever the application could log, they were able to put it into some operational stores. Traditionally, it has been very selective because the data storage was very limited, and we wanted to selectively, very thoughtfully figure out what we want to actually put it in the data. And then at the end of the day, once a day mostly, we do something called ETL processing. What is that? Extract, transform, and load. People in the data warehousing field probably know the term, but many of the other people may not know. It's nothing more than taking the data from operational stores, apply the processing steps, whatever you want to do, quality checks, you want to do transformations, take the raw data, load into a data warehousing system where you can do a transformations, process it, and produce something called a refined data set that ultimately can be used by the consumers of the data. So after the ETL processing in a batch fashion, after the end of the day, you load into various target stores. You build maybe OLAP queue on the top where you can drill down and build reports and dashboards and things like that. Or you can put it in a sandbox environment where a data analyst can play with the data and run their models and derive insights out of that. Or you put it into some historical data warehouse where you have other data you want to join with and maybe do some other processing. So those are the various things you do after you traditional ETL processing step. So what do you do after that? So essentially you run these models. It can be a simple reports, it can be some sophisticated machine learning algorithms, it can be R, SAS, or simple SQL based, whatever it may be, or run some deep machine learning algorithms if you want to. Then finally you derive these insights. So something is happening and that can be leveraged. The insight can drive the business process. So then you use those insights and define some requirements for the applications to implement in the next version. And then you plan for the implementation of that, whatever the insight you derived and that affects the business process or application business function. And then you deploy the new version in the next cycle. So it's called a CSAD cycle, essentially what we call the capture, store, analyze, decide cycle. That's essentially what you're showing here. So this cycle has been working okay for a long time, where storage is limited and computation power was limited, and we were able to do a certain amount of business processes using those technologies. But things have been changing, and this will be a limiting factor if you cannot continue like this anymore. This is essentially the same as what I just described. So what are the limitations of these traditional cycles? It is time to insight is very long. So by the time application produces data out of a customer's activity or some real world activity coming out, and by the time you derive insight, it's several days. Traditionally, it's even more than several days as well, because in big enterprises, each piece will be owned by different lines of business and different teams. Then there is a clear division of responsibilities, who will get the data first and then you transform and then hand off to the next teams. So by the time analyst actually gets the data he wants, it will be a few days or even weeks sometimes. So that is too long in a modern world, that we cannot really wait that long to get dev insights anymore. And also you spend several days to process the data and then clean it up and shape it, and so that it can fit into the model you want to run those things. And this is not really suited for the today's business environment. It cannot continue that anymore. And this model surprisingly not changed even after the big data revolutions. How long is the big data first version of Hadoop? Like almost 9 years ago, right? For last so many years, we have been using these new technologies, but we have not changed the business process, how we use the technology and affect the business. The only thing the big data offered is store larger amount of data and process them at cheaper cost. So it enabled to do that, and that way we are able to collect more data, process more data, but this the batch oriented nature of this process CSAD cycle has not changed much. So now that there is actually a big paradigm shift is happening. Last year and a half, maybe maximum 2 years, things have been changing a lot. So what is this paradigm shift? There's a new buzzword called fast data that's emerging. It's almost a year and a half old that it's gained a lot of momentum. So fast data is like a big data 10 years ago or 9 years ago. And I will explain what's the real time versus batch, explain in a little bit more simpler terms using some analogy, and then introduce what is real time analytics, what it about, and then describe some real time use cases beyond what we actually using one use case, but there are a lot of different use cases. So what is fast data? Fast data is a new buzzword, but basically it is characterized by it's a high speed data coming high throughput, and then needs to be processed in real time as they come in, not store and process it later, but process the data as it comes in on the fly in real time. So that is essentially is one simple description of the fast data. So as I mentioned before, big data last 8 or 9 years or 10 years ago didn't change the paradigm of actually how data be used. So the big data is nothing but essentially higher volume and higher variety of data we can store effectively compared to the traditional databases, and velocity is also component there, but it was not given that much attention. Only in terms of the actually volume, how the velocity contribute towards volume, nothing more than that. So larger data sets stored cheaply on a commodity hardware which are not proprietary and is horizontally linearly scalable. So that was the crux of the big data for last 8 years. So fast data is essentially characterized with the high speed data coming in real time and should be processed continuously, not like a batch, not like an intermittent, but data comes in and then you process continuously. So that is the real description of what a fast data means. And another property of real-time data processing is unbounded. There is no end to it. There is a beginning, you start, and then that's it. So there is a continuously data processing happening 24/7. That is the basic property of the real-time data processing. And high speed and low latency. So you don't want to spend too much time processing 1 or 2 records. You need to keep up with the data coming in. So you have to run at high efficiency and low latency. And in some cases, use cases, you might take a little bit more time depending on the use case. So latency by itself is not the primary criteria, but that's one of the criteria. But the semantics and the capability is much more important than latency, or as important. So here is a little example of what a batch processing looks like in terms of the water heater. How we everybody here have a water heater at home in the basement or the attic somewhere. What you do is you collect that data in real time. It's a water in this case, and you store in a warehouse, in this case a tank, and then you process, you heat it up, and then finally after the water heated to a certain level, you consume it. That's kind of a high level description of the batch water heater look like. So what are the basic properties? You store first, and you process it, and then you serve it. So that's the store, process, serve model. What's a real-time water heater looks like? This is called the tankless water heater. Probably you might have seen or known or might have used. What it does, essentially, there is no tank storing the water, heated water. All it does is essentially, as you use the water, it heats for you in real time. So there is no storage and no need to wait for the water to be heated, and the volume and velocity of the flow should be compatible with the capacity of the heater and the amount of that water you want to consume. So that the parameter you need to adjust. So this process essentially is one representation of the real-time water heating, which kind of describes what data processing also looks like similar way. And this model is process the data as it comes in, and you serve it, and then probably you store it later. Here the storing part is not described in terms of the water analogy, but for our data processing world, after you process and you run your analytics algorithms in real time, you still want to keep a copy for historical reasons. So you still store like a traditional data warehousing we used to do. So what's the real-time analytics? It aims to reduce the traditional cycles of CSAD from weeks and days to minutes and seconds, sometimes even sub-seconds. The problem with the traditional batch analytics is like data is old by the time you use it or consume it, and it becomes stale. So it is too slow for this fast-paced world, as I said. And then real-time analytics will address all these issues, and then let's look at some examples that will get a better idea of what I'm talking about. Just before going into describing our use cases, I just wanted to throw out a few use cases, some financial world and some also from non-financial world. So what is the real-time use case look like? Real-time fraud prevention. So you might have known about fraudulent activity on credit cards often happen, and then what companies used to do, like companies like Capital One, they have this batch processing. They go on the old records, old transactions, and run these algorithms in a batch fashion and detect something might be a fraudulent activity and then flag it. So if the customer can detect it themselves and then call back and say that, okay, that's activity, it's not my transaction, but somebody posted it fraudulently, then they will flag it. But they also have some algorithms they can run in a batch fashion. But problem with that is that it's too late, it's already happened. So it's too costly to fix something which already happened, too expensive. And sometimes you may not be able to recover the money or whatever transaction happened. But in the fraud prevention, you can actually check against the fraudulent knowledge base every transaction in real time. As soon as you swipe the credit card, it can go against the rule base, check against certain rules and make sure that it is not a fraudulent activity. It doesn't guarantee 100%, but 99% of the times, a lot of fraudulent activity can be easily detectable actually. So one of the example is that if your credit card is used within a few seconds of the apart, two different transactions, two different locations, and geographically apart, maybe different cities or different states, it's physically impossible for a person to be two places at the same time, right? So these are the things you can easily detect, and you can automate it and you can detect in real time. So every transaction can be checked against this fraudulent activity before it can get approved. So you are actually preventing the fraud. If it is fraudulent, then you can actually deny the transaction. It's much more efficient, much more cost effective. It saves a lot of money and it is makes customers happy as well. That's one example. And then many such examples in financial world I can give is that second look at duplicate transactions. Sometimes you swipe the credit card at the point of sales and something goes wrong, whether the machine is wrong or something else happened and you have to do it again. Sometimes that ends up duplicate transactions. So you can actually check those things in real time. So you can actually inform the store clerk or even the customer back with your message, text message or something. Before you step out the store, you will actually get a message saying that, okay, something happened, go back to service desk and fix this before you go home. You don't have to come back later and fix it. So these are the things we can do in real time now. The technology is available, you can actually do it. And another example is the real-time credit line increase. Like some of you might have experienced this. If you go to a store and try to buy like a large ticket item, right? And you may not remember exactly how much credit limit you have currently and how much is used up for that month. So it's possible that it goes over a current credit limit. And the way currently it happens is that if it goes above the limits, the transaction is denied obviously, because that's how it set it up. So what happens, somebody has to make a phone call. Either you call credit card company or the store clerk calls on your behalf, or you have to do a lot of this processing manually, and then maybe a lot of time delay, and then either maybe you get approved or maybe not. So that's nothing to do with your credit worthiness. It's just that the way it set it up, and it takes time for them to actually increase that. But currently we can actually trap this credit line exceed events in real time, and then if that happens, you can actually make sure that customer is credit worthy and then increase the limit temporarily for the transaction and let the transaction go through instead of preventing it, and then work out the actual permanent increase with the customer later. So what's the result of this? All the three players who are otherwise unhappy if the transaction is not gone through, store loses business, credit card company loses a commission, customer doesn't get his purchase. So all three players are unhappy. But if you are able to do this one, all three people actually players come out happy. It's a win-win situation. Everybody will be happy. So it's possible to do that now. The technology is available. So there are other things you can do. A lot of marketing based on real-time behavior of the customers and shopping advice, and if you are interacting with banking or any other financial applications and you are not able to perform your activity, it can detect using the customer activities in real time and then try to assist you. There are lots of other use cases. I didn't really list all of them, but some non-financial world. So Internet of Things is coming in a big way. All the appliances and devices are becoming smart, and they are sending real-time data, generating events in real time. So those are the big opportunities to use the real-time technology to process those. And the system monitoring and failure prevention, instead of waiting for a system to go down, you can actually constantly monitor them, and systems cannot just fail without warning. There is always some things you can detect before they actually fail. So if you can detect in advance, a few seconds or a few minutes, then you'll be able to transition to a new system or fix the things which is going to fail. So those kind of things you can constantly monitor in real time and then prevent those failures. And connected cars and automobiles, that's another big thing happening. Airbus has 10,000 sensors on its aircraft. So it sends constantly, every sensor is sending events constantly. So there's a large amount of data that can be detected, collected and then analyzed in real time. So constant monitoring and feedback and continuous learning from the driver's behaviors. So driver can carry a sensor with him. Some of the insurance companies now started having these pilot programs where you sign up for that, you'll get a discount on your premium, but they ask you to carry a device in your car with you, small device, that will give all the information about your driving activities. So if you're a safe driver, you don't mind sharing information, you sign up for that, you'll get a discount on your. So these are the kind of things you can possible right now. So what are the drivers? We already touched upon a few things. So there are like 4 categories of the drivers that driving this towards real time. So what's the business drivers? The business environment has been very competitive, and business need to react quickly to any changes happening in the marketplace or customer behavior or competitors space. So if you don't do in time, then you probably may not survive in the current market. It's very competitive. We know a lot of examples of big companies just disappeared. I mean, don't exist anymore. The ETE, Bell Labs or Lucent Technologies was the original inventor of the telephones. Don't exist anymore. It was just absorbed into some larger company, a European company. Kodak is an example. I mean, they couldn't react in time and they disappeared pretty much from the market. And also customer expectations are changing. They don't want to wait long time for them to be served for any changes they expect to happen. They want it to happen now. And those things existed before, but because of the technology was not available, we could not really do all the things we wanted to do in real time. So now technology is available. That is what is driving. So as I mentioned, big data for the last 10 years, that Hadoop, which started it all, did not change the analytics model. It only enabled us to process the large data at cheaper cost. But new advancements are happening in big data world. Hadoop is not the only technology anymore. There are lots of different flavors. There are different new tools are coming up. Apache Storm, I started this trend like 5-6 years ago. It was a tool that allows you to collect events and process in real time. That was a big game changer. The Spark came along, and Spark, even though it's not a real-time processing engine, it adapted something called a micro batching, which collects events into a small batches, and every few seconds or every minute, whatever the interval you want to configure, it simulates the real time. It's not a real time. Then a new tool which I just mentioned earlier is the Apache Flink, which we use. It is a true real-time stream processing engine. It processes event at a time, doesn't do the micro batching, and it has a lot of different characteristics. I don't want to go into details. It has high performance, it's a distributed, fault tolerant, all this good stuff you associate with big data technologies is still there. In addition to that, it gives you the true real-time processing engine. Essentially, it's a combination of the Storm and Spark in one, plus more. It offers much more than a Storm or Spark can offer. So as I mentioned about the technology like a Flink or earlier versions like a Storm are driving this towards real time, and then business need to react quickly, and the data is becoming obsolete as fast as it's generated, so you need to consume it. Fast data is like a fast food. If you don't consume quickly, it becomes stale and useless. And the social trends, this is one of the things kind of caught my attention when I went to a dentist office. So it's a toothbrush currently they are selling, and it has something called real-time feedback. What it does, it has an app you can actually download on your smartphone, and it has a Bluetooth connection. While you are brushing, it actually generates events every time you stroke, and then it counts all the activity. It knows the position of where you are brushing, It gives you real-time feedback. If you forgot to brush certain part of your teeth, it will tell you. If you are brushing too long at one position and forgot, maybe thinking about something else while brushing the teeth, it will let it inform you. And it looks funny at the time. I couldn't believe myself actually. Is it really useful? But apparently clinical trial proved that it has 200% improvement in the effectiveness of the brushing. So it's their claim. I have not checked any of those things, but I'm just showing this an example of the social trends. People want real time and companies actually are trying to offer that. And a lot of new industries I mentioned about and also driving that new type of real-time data generators are coming in and need to act real-time. The connected cars and automobiles, the future is going towards driverless cars essentially, right? But even before going that, even current cars generate a lot of data. Not all the current cars actually have they are connected yet, but the new generations are coming already. They are pretty soon in the market, many of them in the research phase. But if you ever driven the Tesla, the last week I drove one of those, Tesla already has those things in place. They are ahead of everybody else. Maybe Google car has one, but it's not in the public market yet. So Tesla is available, they are in the public, you can go buy one. It has a lot of things built in. It generates the data, lot of sensors, I don't know exactly how many. It sends constantly all the data to cloud. And if it has something called autopilot mode where it's not like 100% driverless car, but at certain segments, if you're on highway, then you can put in autopilot mode. It can actually do automatic steering. You don't have to touch the steering at all. So it's pretty much halfway there in complete automation, but it's not completely there. But if you're going some road and if you find a ditch and it didn't know before that and you're trying to steer away from it, it learns that instantly. So next time you go on the same road, it will actually automatically steer out of that particular obstacles. So it's constantly learning while it is driving. So these are some of the drivers which is kind of pushing towards real-time data processing. Again, social trends, I showed example of the toothbrush. But then in general, what's happening, like with the smartphones, everybody wants everything instantly, push of a button. That's kind of a high-level view of things. They don't care how much data processing required, how much complexity is there to get it done, anything, but you don't care. Like for example, you want to translate a piece of a couple of lines of a foreign language text to English or English to some other language. You have a Google Translate app on your cell phone and you expect it to happen instantly, right? But some of you might have heard yesterday's keynote address, how much complex it is to really understand a language and translate it. It involves a lot of data processing. But we don't care. We just wanted the answers back with the push of a button, right? So that's the demand of the user's behavior. So this kind of set the stage for why this thing happening. And a little bit about Apache Flink. I don't want to spend too much time, as I said. If you want more details, so you can, I'll give you links where we have a lot of information available. So this is a view of how the big data for last 10 years has been evolving, right? So Hadoop and MapReduce was the original big data creators. That started by this Apache project, and it was actually originated in Google. They published some papers, and then these guys implemented in open source an Apache project. So that's how it all started. So what is the basic characteristic of it is, well, it's a batch, and you essentially use one tool called MapReduce. It's like a specialized way of writing programs in Java. Very highly data parallel applications you can write easily. And if you try to write anything else in MapReduce, you go crazy and you probably never achieve anything useful. So it suits certain corner cases of data processing, but a lot of traditional data processing fits into that mode. So it was fairly successful in terms of processing in MapReduce as well. But its major contributor is that it's basically linearly scalable system where you can store data cheaply using commodity hardware. So HDFS as storage and MapReduce as a processing. That's the first generation. So what happened next? Once you have the data, people want to use it, right? And there is no way to use the data in Hadoop using interactive methods. You have to run a batch job and extract the data and use other tools to really consume it. The people started trying to find a ways to improve the performance. You can sit in front of Hadoop system and want results back, want to send a query like an interactive SQL like or a traditional database like behavior they want. So there is something called Tez was introduced, which allows you to do interactive queries instead of MapReduce. It has its own engine that will give you much quicker. It's not like a very fast, but it is fast enough that you can sit in front of terminal and then interact with it. So that was enabled by the Tez. And then it also added a few more other things like data flow graphs and things like that. So that's the second generation. It's essentially speeding up the MapReduce, which is a batch. The Spark came along. I didn't put the Storm here because Storm is not a general purpose engine. It is very specialized for stream processing. It does only one thing, whereas these tools are general purpose data processing engines. So Spark came along. Spark also is a batch engine, but they are able to do near real time by simulating real time stream processing using a micro batches. Batch events into a few seconds of events into a batch, small batch, and then you do the processing. So it was able to do interactive processing. It uses the in-memory algorithms, out-of-core algorithms, and automatic memory management and things like that. So with a few techniques and a few innovations, they were able to provide this near real-time kind of behavior. And then the Apache Flink is what we are calling as a fourth generation, 4G of big data analytics stack. It gives you the hybrid. It can do streaming and batch, and it can do near real time or completely real time, event at a time, and then it can do a lot of other things as well. So it's kind of a next stage in the evolution of the big data analytics stack. So what is the high level, what the Flink is doing essentially is that taking the two different worlds. So we have on the left side what's called MPP database technology, where technologies like a Teradata or all these high performance database engines. Last 30 years we have been using this technology, and this evolved and it's pretty mature. A lot of nice things they actually invented, database technology. So there are a lot of things like a declarativity. You can actually query SQL queries like more declarative. You don't have to worry how query get executed, where it is running, and how algorithms are working. You just declare like a select few things and apply few filters using some SQL language. So magically it does all the query optimization in very efficient execution in parallel. A lot of good things it does. And Hadoop brought along a completely different set of properties. It's in massively scale out. The traditional MPP database, it scales, but it's very, very expensive after some time. But there is a limit. You cannot really scale. Whereas Hadoop, infinite scalability. Keep adding nodes and you can keep getting more storage. That's all it is. Also, it has a much more complex data types and user-defined types and schema and read. You don't have to think the schema in advance, whereas the traditional database, you have to have model in advance to be able to even start putting data in. So the Flink is trying to combine both and add few more goodies to it. That's essentially what this Flink offers. It has all the properties of the traditional database. It has automatic query optimization. It has a declarative programming language with a Scala, and the API they created is a very high level declarative style. You don't specify how, you just specify what. And it has the same properties as the Hadoop in terms of the scalability and schema and read kind of thing. And also adds in the middle things, real-time stream processing. It has iterative processing in memory. And then automatic memory management. You never run out of memory and memory out of memory exceptions in Flink. They don't use Java memory manager. They do their own memory management inside Java JVMs. And it also has a lot of advanced features like data flows and graph processing APIs. This is another view of the technology stack here, what the Flink look like. On the bottom layer, it's a storage layer, right? So Flink can work on any type of storage. It can be a local file system, or it can be a traditional HDFS. You can use the HDFS Hadoop file system as it is, or it can be any other storage technologies like Amazon or Microsoft Azure or any other. And it can be a database also. A storage can be a database backend. Flink doesn't care where actually the data is coming from. And it also integrates with a lot of different sources. So it doesn't have to be a storage, actually a source. It can be a a data stream coming as a source. It can be a Kafka, it can be another message queue, it can be Flume and things like that. So that's where the data comes from, or it get data goes to as a storage endpoints. And then that's where you deploy. You can deploy on a single JVM, or you can deploy in an embedded application. It can deploy in a cluster on your premise, or it can deploy in a cluster in a cloud. So you have different ways of deploying that. So at the core of Flink is a stream processing engine. Even though it also do batch, it treats the batch as a finite stream. So batch job essentially has a beginning and end. So it creates a stream which has a finite length. In real time, actual real stream processing, you do not have an end. You have a beginning, but you never have an end. Whereas a batch has a stream with a finite limit. That's all it is. So it treats everything as a stream underneath. It's the core of the engine is the stream processor. And then it has two different APIs. So it's a batch API, data set API, and stream API is a data stream API. But both will be translated underneath into a same common engine called Flink runtime. And then for the batch API, you have much better optimizer because it knows the complete data set already. It's a batch. Whereas stream, you don't really know the end data. You cannot do as much optimization as you can do in the batch, but it can still do some optimization. So now we have these two different APIs. So what can you do with these APIs? So if you already have a Hadoop installation, a lot of MapReduce jobs running, you can run the same jobs on Flink, no change. They provided something called a compatibility layer. So you can run MapReduce jobs, and you can run existing Storm jobs, and you can run something called a Google data flow. I don't know if you guys are familiar with it. Google offers something called data flow API that can be used for running applications in Google Cloud. Now they are putting that out in a public domain. So it's become Apache project. It's called Beam, Apache Beam. Beam is nothing but a batch and stream together into one API. So Google created one API for batch and stream, but if you run in their cloud, they have two different engines underneath. Whereas Flink is essentially a little bit opposite. It has two different APIs, but one engine underneath. Now they are trying to bridge these two into one. Maybe in the future, we'll have one API for batch and stream, and one engine underneath running it. So this is kind of very high level. I'm not going to go through details of each of those capabilities. There are a lot of different things you can do. You can do machine learning, you can do SQL, you can do graph processing engine like Jelly and things like that. So that's kind of a background about why the shift is happening towards real time, and what are the technologies, and then specifically a little bit more about the Flink. So what's our business case? So this is the crux of the talk essentially. I just set up the case for it, what we are doing. What we do essentially is customer activity event logs. So these are the events we collect from customers' activity on our digital platforms. So whatever the customer does, we essentially collect everything. The customer activity events are not click streams, even though we collect those as well, but these are the business level events. So we collect, like if we try to log in, trying to pay a bill, trying to transfer balance, all these business level activities, we collect them. So those are we call customer activity logs. So why we are doing that? Because that tells everything about what customer is doing. It's a digital footprint of customer activities. So everything we want to understand customers, we use this data. And this is a standardized way of collecting events. We use the same standard events across all applications, whether you are using a mobile app, you are using a web app, or you are using any other means to interact with our platforms. We collect in a standard way. So use this data essentially to provide a better customer experience and make sure that our systems are doing what they're supposed to do, and how we can improve them. And also we use for a lot of other things, for example, maybe targeted marketing and things like that. So this is the architecture we implemented. So as you see, there's so many open source tools we stitched together to make a end-to-end solution. So going from the left here, we have systems producing data, and we collect using something called Apache NiFi. It's an optional tool. It doesn't have to be there. You can directly write data into Kafka and then consume it. But NiFi offers us some few things which you can use if you want to. Things like on the fly encryption of certain fields or masking and things like that. It lets you do that on the fly. Events comes in, you take out some fields or add a couple of fields, encrypt them, and then feed into Kafka. So Kafka is the main broker we use. It's a scalable, fault-tolerant message broker. It decouples producer and consumer, and if your consumer is down for a days, it will still keep all the data. You won't lose it. It guarantees you the data, and when you connect back next time, it will replay back all the data. It is queued up for you, so it knows where you left off, and it can replay back for you. So that is the reason why I use Kafka. It has a persistent backend. It can store based on the capacity, days or weeks worth of data if you need to. So it's very critical to have that component if you are running a 24/7 data pipeline, because things can go down, or you might want to bring it down for maintenance, downstream component. You need to have a way to store the data enough so that you can get it back. So the core of that, after the Kafka message broker, is the stream processing applications we built using Apache Flink. So some of the things we have done here is, I'll go into details of those things, but things like real-time alerts. So if you find something, immediately alert, sending into Amazon simple notification service, SNS, then anybody can subscribe to it. It can be a text message, it can be email, or it can be combination, it can be something else. So SNS is a very versatile messaging notification service. Just send it there, and then it can distribute to other recipients. Then we have a time window based aggregation. Flink allows you to, in the real-time processing, you need to have a way to define a window where you want to focus, continuously moving window. So it's time-based, it can be count-based, it can be a combination of that. So let's say if you want to find out every 10 minutes, what are some other things happening, how many people logged in, how much money has been moved, or how many people have failed to log in, things like that. So you can collect that. And then we also do on-the-fly transformation and enrichment. We change the data format, we flatten out, we make different kind of transformations. And then we also add extra data which is not in the event coming in. We take from other sources and then just enrich it, so that the downstream consumer doesn't have to do a join later. So they just think it is coming from the original source. They don't care. So those are the few things. And then we index into something called Elasticsearch. It's a real-time indexing and searching database. So it can let you search through the data in real time, and it also can insert data in real time at the same time. So we have that. All the streams we generate, we index and put it there, and then we have a GUI built using something called Kibana. It's an open source tool, allows you to view data, visualize it, and then do some queries and things like that. And we also store a copy of the data in a Hadoop file system for a batch processing later. So that's kind of a high-level view of the architecture. So these are the few features we implemented. As I described about alerts, enrichment, transformations, aggregations, and indexing and search. And we are also in the process of designing machine learning algorithms. You want to dynamically load in real time so that you can apply those models as data comes in, so that you can continuously improve those models. So some implementation details. So this is what we set up. Essentially a small cluster we set up on the cloud, Amazon cloud, and we used our mobile data set coming out of our Capital One mobile application. So how that alert works, essentially when the event comes in, every event individually we check against a set of rules, and it matches a rule, we notify right away, before you do any processing, before you do indexing, before you do any transformation. So that's the first thing we do. One other thing we use this for is fraudulent device notification. So there are certain devices which have known to be fraudulent. So if you see somebody trying to log in using those known fraud devices, we right away alert. We don't want to wait for anything else. So we don't want to wait for the batch or somebody analyzing later. Right away, he's trying to log in using a fraudulent device, we prevent it or notify somebody. So that's an example, right? Enrichment. So as I mentioned before, we have a source of data where we have a event has something called event ID, and we want to add event description which is not in the original event. That lookup table has that mapping of the ID to description. So we take the description and add it to the event. So the downstream components like GUI don't have to go and look it up in another table or another database to figure out what the code means. So for users, it makes more sense to use this English descriptions than the numbers. So we add this enrichment. This is an example. We can do a lot of other enrichment as well as extra information about a user. The event comes with only user ID. It doesn't have any more information, but we have a lot of data about a user. We can bring it all and bring it to the stream, actually add them. And transformations, so our event structure has a certain standard elements and certain variable components where those variable components varies based on the type of event. So those variable fields are actually not at the top level attributes, they are actually a lower level, but as a transformation we flatten them out. We make it as a flat table so that searching becomes easier for the downstream tools. This is another component very important the Flink offers, window-based aggregation. So here we are defining a sliding window of 2 seconds size, and it refreshes every second. It moves second by second, but its size is 2 seconds. So every 2 seconds worth data, you can apply aggregations. You can count, you can find averages, you can find maximum, minimum, whatever counts you want. You can do all these things for that particular window. And the window keeps sliding every second. So at any time you will have a 2 seconds worth of window, you are counting aggregations. And Flink offers much more than the time-based window. It also offers a count-based window. You want to count until every 1,000 events, and it can be a varying time length. So you can have a custom window. You can define your own window mechanism. So these are all very flexible windowing system available here. So this is a GUI, Kibana, where we display the information that is indexed in real time and put it into Elasticsearch. So we build dashboards and searching queries, exploration essentially. So this one is a widget based GUI, and then this is the what's called a discover window, where you have a toolbar on the top. You can allow you to put queries. They are not SQL queries, they are a little bit different, but they are very intuitive and simple to understand if you learn this. So you can search through the query, and then it displays the data, filters out, shows only the data set that hides that search criteria, highlighted with the yellow. And you also have a time series graph on the top. So if your event has a time attribute, it will actually display this time series based graph. You can zoom in, zoom out of this window. Either it can be days or it can be minutes or seconds based on whatever you want. You can also use the mouse to select a portion of the window and then expand it. It will actually blow up that particular interval throughout the window. And then just a comment about the architecture we have created. It's not really specific to our use case. We found that many real-time use cases actually follow this pattern. So what essentially we do in real-time data processing is, you have events producing data that can be anything. It can be applications, it can be devices, it can be servers, it can be appliances at home. They generate events, and you have event collectors. You need to have a way of aggregating various sources into fewer sources. And then you have a message broker where events are put into a broker so that it can serve to the actual consumers. So it's a kind of in between producers and consumers. And then ultimately you need a processor. So what good is the events if you don't really process and derive some insights out of it? So event processor is the core of the whole real-time processing application. So, and then you have some ways to store the data, your process, so that the front ends like dashboards can actually look at it. So the general pattern. Then some other things, when your event processor finds something notification, it has to send it to notification service somewhere, notify somebody. And then sometimes the event processor can actually send a message back to the application saying that certain thing happened. The application can actually take an action without some human being notified. You can notify your applications. So depending on the insights you derive, those can be actionable right away. You can actually send an event to the application, they can act on it. And then you can also have a way of loading some learning models, updating them, dynamically loading them. So that is another common touch point. So this kind of high level architecture, and at every stage, everything, there are many options for the tools. You don't have to have one tool. Of course, some tools are better than other depending on your use case. So for example, event collector, there are a bunch of things you can use, Flume or Spring XD or NiFi or other things like Logstash. Event broker, we use Kafka, that's much more versatile, but it don't have to. You can use RabbitMQ or any other messaging queues. Event processor, this is where we pick the Flink, but you can potentially do with Spark as well, but it has its limitations. As I mentioned, it does not alert based on a single event. You cannot do that. And its window sizing is very, very limited. It has a micro batch size, and your window has to match what the micro batch size is. You cannot do anything. It's not very flexible. Again, so indexer, we use Elasticsearch. It doesn't have to be. It can be Solr. It can be another NoSQL database like Cassandra. Or yesterday I was attending another talk. Somebody talking about FolioDB. That's another option. Maybe we will take a look at that. Dashboard also, we used Kibana, which is readily available, but you don't have to use that. So that's kind of a high level view. I don't know how many minutes I have. So another 3 minutes, I'm going to stop, then take questions. So I just put together this diagram where it's a analytic spectrum. So it's a batch and real time is not just one or other. It can be, it's a spectrum essentially. You can derive some insights right away quickly in real time. So as you process more and spend more time and increase the latency, you will probably get a more and more better insights. So there is a compromise at every stage. You can actually, whatever the insights you derive, you can actually send it out. The more you process, the more time you spend, you add some latency, but you get a better insights. You have to find a right compromise for your use case. How much you want to do in real time and how much you want to do in a batch. So it's essentially a combination, it's a spectrum. It's not one or other. So that's essentially my talk. Is the last few takeaways. Traditional batch analytics is not suited for the current world. It has a long intervals, time to insight is long. And business and technology and social drivers changing the paradigm, and everybody moving towards the real-time data processing. And the new technologies like Flink are essentially fueling this trend. Need to enterprise to react events to real time as they happen, not wait and act later. And the future competitiveness of business rests on the ability to capture, store, and process a large amount of data in real time. So that is a must, is not an option. So paradigm shift towards the fast data is happening across enterprises. It's not an option. Again, they said there is still room for a batch. So certain deep learning analysis and things you cannot do in real time because of the latency issues. So it is essentially it's a continuous ETL. It's a continuum of the data processing from one end of spectrum is the batch, another end is the real time. There may be in between as well. So that's about it. Thanks for your time. And if you want to have any questions, hope I have some time here.
Hi, you mentioned about alerts in the Flink. Does it provide out of the box, like, or you implement like code there, like coding part there, like alerts part, which you are putting?
Alerts, yes, it has a built-in alerting mechanism, so you can specify what you want to alert on. It will do it. So that comes out of the box. When we implemented, we used the 0.9 version. At that time, they didn't have the alert API. But now, 3 weeks ago, they released a 1.0, which has an alert API actually built in. It comes out of the box.
Like some of the constructs like notifications and all available there, SNS, or you manually pointed the SNS topics and other things like?
Right. So the notification service, send it to SNS, we have to point to the SNS. It doesn't come out of the box. But there is an API, alert API. You have to call that and specify the condition, and then you specify the target where you want to go to. It will send it automatically.
Okay. Another question. So you mentioned about NiFi.
Yeah.
So NiFi is like a processing layer or a data collector? Is it something like?
It's a collector. It does a little bit of processing, but it's not meant as a It's not something like a Flink or a Storm or a Spark. It doesn't do like a heavy processing. It's not a general purpose processing engine. It's a tool to put together data flow pipelines, but you can do simple things like on the fly encryption. So take a field, encrypt and replace with the original one, you can do on the fly. You can do simple things, but it's not really analytic engine. You cannot do, let's say you cannot run machine learning algorithm, or you cannot do complex windowing or aggregations. You cannot do any of those.
Thank you.
Have you run into any use cases where you have to do reprocessing on your event stream?
Pre-processing an event stream.
Yeah, where you had to like replay events and run it through, a second time.
Yeah, we haven't used any such use cases, but that idea of this real-time pipelines like this is that the same pipeline can be run with a file as a source, essentially act as a batch, right? So you don't need a separate engine. That's the whole idea of that Lambda architecture yesterday somebody was talking about, has to have two different engines for batch and real time. But this is essentially one engine can do real time and also batch processing. It's everything in one. You don't need a separate pre-processing. You just build into the same pipeline.
Okay. And just one other question. I'm just curious, what led you to pick Elasticsearch as your data store for all your stream data?
That is I think just for the simple reason the Flink came with the Elasticsearch sync out of the box. So if we can write to any other database, but just we have to write extra code. It's not too long, but it came with it. We just used it. That's all. Okay, no other questions? Thank you.